In the last video, we took a look at how we could actually determine the amount of work that was done by a vector field on a particle moving along a line or along a curve. And we came up with the following. We said that we would have to do force dotted with the unit tangent vector ds. And you can go back to the last video to see where that derivation came from. But we also said that that would be very difficult to evaluate. And so we simplified it down to this formula, which we also said was equivalent to this last formula, although we didn't really explain why yet. So let's take a look here at example 1 to see how we can maybe put all this information together and understand how we can utilize it. So I'm going to find the work done by this force field in moving a particle along the line segment C, which goes from 2, 0, 0 to 3, 4, 5. Oh, very interestingly, this is actually the exact same curve as we had in example 5 back in section 521. So if you have those notes, you could even go back and pull those out and take a look at how we could easily come up with a parameterization for our curve here. So I'm going to go ahead and just start with that immediately. I know this. We know a parameterization for C is, well, and that would be R of t is 2 plus t, comma 4t, comma 5t. And again, I'm just pulling this right from example 5 in the previous section, so that way I don't have to redo all the work here. Okay, great. Once I have this, notice that means I can easily go ahead and calculate the amount of work that's done by setting up the integral. Now, again, this first integral, while this is how we derived it, it's never how we're going to use, or never what we're going to use to compute the integral. That'll be the second one, which is why we had to simplify down to that. So I'll say this. By the above definition, we know that our work is going to be equal to an integral from a to b, so that's from 0 to 1, and it's going to be of f evaluated at like our R of t information, and then dotted with our R prime of t dt. This is what we have. Okay, so this is going to be kind of messy. We'll have to think about how this works. So what this means is I'm ultimately going to have to go and in place of my f function, which notice here has my y, z, and x in it, I'm going to be plugging in what my R of t components are. So I'm going to plug in 2 plus t for my x, 4t for my y, and 5t for my z. Then I'm going to go ahead and dot that with the derivative of my r. Well, the derivative of my r is pretty easy to spot. That's 1, 4, 5. And then I'll have just dt at the back. So let's go ahead and continue to simplify this. Notice here that I'm going to end up with an integral from 0 to 1. I'm going to think about what my vector f looks like after I replace y, z, and x with these values here. It looks like it would be 4t, 5t, 2 plus t. And I have to dot that with 1, 4, 5 dt. When I do this dot product, of course I know that I end up with 4t plus 20t plus 10 plus 5t dt. If I simplify that down even further, I realize that's just going to be 29t plus 10 dt. And I'm going to equal this to, let's see, 29 over 2 t squareds plus 10t. And when I evaluate from 0 to 1, I get 29 over 2 plus 10, also known as 49 over 2, or 24.5. So we can immediately do this evaluation, but something really crazy should actually pop out to us. If you actually did go back and look at the previous video or at the notes that you maybe had recorded for this 5.2.1 example, I would ask the question, what was our answer on that question? I'm actually going to pull it up here and take a look back. Okay, so here was the question. Suppose that C is the line segment. We evaluated this thing, and our answer was exactly the same. Here's the really crazy part. That is not a coincidence. There's a reason why we ended up with the same exact thing. If you take a look at the next page, you can see maybe why. I'm saying that I believe that we can view our resulting work, instead of in this weird integral form, I think we can view it in this form. And this form, you might notice, is the same as what we had in the previous section. So no wonder the answer is coming out identical. Now, in order to view this a little bit more simply, I would go ahead and state the following. I'm going to say that if we think of dr, notice this is a differential, but I have like a vector above the r. So it's like, I know I could take the derivative of my r of t, but I'm just going to not have the dt portion in there. Let's say I think about my dr as a dx, dy, dz. Okay, let's just suppose I think about it in that way. You can almost kind of imagine maybe where that would come from, because if I did dr dt, that should have been equal to dx dt, comma dy dt, comma dz dt. And so if I kind of imagine multiplying everything on both sides by a dt, I'll arrive at exactly what I wrote down here. So I'm going to go ahead and say that if I think about this, we see that this w, which is equal to y dx plus z dy plus x dz, I could imagine writing as a dot product. Specifically, a dot product of y, z, x dotted with dx, dy, dz. And very interestingly, I can see that one of those pieces is definitely dr. But where does this piece show up? It doesn't show up on this page, but if you take a look back, that was exactly f. So this is another way that I can think about this sort of mixture of line integrals. So this allows us, this kind of reinterpretation of dr helps us maybe make sense of what we actually have over here. That I could imagine computing this work integral, doing this f dot dr. So I can actually then see that when I'm computing work, the line integrals with respect to x, with respect to y, and with respect to z actually show up. Like I have to consider how much change or motion exists in all these different directions. So that's a really, really, really cool and powerful idea that helps us draw this connection. We'll see how we can actually use this idea directly in the next example in the next video.